Okay, we're looking at limits as x goes to infinity. So I went ahead and graphed in my my function 3x squared over x squared plus 1. And you can see that this graph looks like it goes towards an asymptote. On the right-hand side, I end up with an asymptote that's at 3. And on the left-hand side, I also end up with an asymptote at 3. So I went ahead and filled in the table for you. And you can see that on the left-hand side, so as I approach on the left, we're getting closer and closer and closer to 3. But remember, our actual value isn't 3, but we're close to 3. So what do we call that? We call that the limit. So our end behavior as x approaches negative infinity is going to be 3. Okay, so this one, as x approaches infinity on the right-hand side, again, this time I collected the values on the right-hand side, and you can see that we're getting closer and closer to 3. So it's really important to remember about limits at infinity that we're talking about the x values. So on the ends, another way we're talking about this is the end behavior of the graph. So just like we did in rational functions, this is the end behaviors. So we had some rules for end behaviors. Remember Bobo, Botan, and Eats DC? This is them. So if the denominator is, so if it's bigger on the bottom, so the denominator is bigger than the degree on the top, then the asymptote is going to be at 0. So it's going to look something like this, with an asymptote at 0. Okay? Let's make it like green. Okay, boom. Asymptote at 0. So the graph will get closer and closer and closer to 0. If I have Eats DC, then that means the coefficients, we're going to divide to get the asymptotes at the coefficients. So something like that. Then your graph will end up going close to that asymptote. So the ends get close to that asymptote. If I have something bigger, the degree on the top is bigger than the degree on the bottom, then we end up with some kind of like slant asymptote. And the graph could look like this, potentially. Okay, so on the ends, you're going towards infinity and towards negative infinity, depending on if you're on the left or the right. So let's talk about how to figure out the limit using some algebra. So the limit as x goes to infinity, so positive infinity of 2x minus 1 over x plus 1, the exponents are the same. So what you do is you take a look at the leading coefficients, everything else you ignore. Then we go ahead and we just divide the coefficients. So 2 divided by 1 gives me 2. This has some sort of end behaviors that are going to get close to 1 on the right-hand side. Or close to 2, on the right-hand side. For B, we go ahead and look at our leading coefficients, 3x over 4x squared. Okay, another way to think about this is who is, like, power-wise, who's going to win? Is the top larger? Is the top growing faster, or is the bottom growing faster? Well, the bottom's growing faster, so we're going to have a smaller number on the top divided by a really big number, which gives me 0. This is a Bobo situation, Eats DC, and then I bet you this one's going to be a Botan situation. Okay, so I'm going to look. 5x squared, x to the 4th over 4x squared. The top degree is larger. So remember I think the easiest thing to do is to go ahead and just divide. So I'm actually going to be taking the limit as x approaches negative infinity of something close to this, which is 5x squared over 4. I just went ahead and canceled out those coefficients, and I canceled those out. So I am going to plug in my negative infinity in for x, so negative infinity squared over 4. Again, you can drop the limit operator because we're plugging in a value. So negative squared would give me a positive. So I get just 5 times 5 over 4. So this is a positive. So 5 over 4 times positive infinity would just give me a positive infinity. Okay, so basically we're going towards infinity. One important thing to remember about bottom is that because the values are bigger on top, we get slant asymptotes, which are either going to send us, the y values are either going to go to positive or negative infinity. Okay, Bobo, all the y values go to 0. Each DC, the y values go to some value where you divide the coefficients to get that value. All right, so here's some extra tricky ones. So the limit as x approaches infinity of sine x. So I want you to think about what sine x looks like. And I remember that it oscillates like this. So as I go out towards infinity, we're just going to keep bouncing. So this oscillates between -1 and 1 and +1. So since it oscillates, okay, so I can just put it here. Since sine x oscillates between -1 and 1, I know that the function, the limit, as x approaches infinity of sine x does not exist. Okay, so we're not going towards one value, and that's okay. Okay, here's a fun one. The limit as x approaches infinity of sine x over x. Okay, and you would think that this one wouldn't work either, but this x is getting larger, while sine x is bounded between -1 and 1. So when I graph this on my calculator, it looks something like this. And you can see that it oscillates, but gets smaller. So and it actually is going to oscillate and get smaller towards 0. So we're going to prove that this works really quick using the squeeze theorem. Okay, so if you remember sine x, like we just did, I'm going to take the function sine x since it's pretty close to what I'm starting with. I know that that function is always in between, my outputs are always in between 1 and -1, right? So my lowest output is -1 and my highest output is 1. I'm somewhere in between this bounded region. And then I'm like, okay, that's cool and all, but I have sine x over x. So I am going to go ahead and divide this by x on both sides. All sides, excuse me. Okay, and so now I have my function that's squeezed between these other two functions. And what I know is that if I take the limit, okay, as x approaches infinity of -1 over x, and I take the limit as x approaches infinity of sine x over x, and that has to be less than or equal to the limit as x approaches infinity of 1 over x. So when I plug in infinity, is this a Bobo bottom or eats DC? That's a Bobo situation because the bottom degree is higher than the top degree. So I get -1 over infinity, which is 0. And I'll leave the middle for a second. Okay. The limit as x approaches infinity of 1 over infinity is also going to be 0. Basically, the bottom wins out. So since sine x over x is squeezed between these two functions, the limit is also going to be 0 for sine x over x. So the limit as x approaches infinity of sine x over x is equal to 0. That one's weird. You should memorize that one. Okay? Okay, lastly, sketch the graph of e to the x. sketch the graph of ln of x, and then find these key characteristics. Okay, so I'm going to go ahead and sketch the graph of e to the x. I know it crosses at 0, 1 because that's how powers work. E to the 0 is 1, and then at 1, the value is like 2.718 because that's e. Okay, so e to the 0 is 1. E to the 1 is 2.718. So as x goes to infinity of f of x, e to the infinity is going to go towards infinity. And on the negative infinity side, e to the negative infinity would be like, okay, a negative exponent is like 1 over e to the infinity, which would give me 0. Okay, ln of x. I know it has an asymptote at 0, and the graph goes something like that. At g of 0, the graph is undefined, okay, because ln of 0 is the asymptote, okay. Ln of 1 would be 0, and ln, so as x goes to infinity, that would be like ln of infinity. The graph is going to go slowly towards infinity. Yeah, slow, very slow. And then as x goes to 0 from the right, that would be like ln. Well, I can see that the graph, looking at the graph from the right, the function is getting closer and closer to negative infinity. And that is that.